Okay, this is Unit 6, Lesson 2, Vocabulary Review. Explain the difference between an event and an outcome. Who can tell me the difference between an event and an outcome? Yes, Tori.
An event is a collection of possible outcomes, and an outcome is the result of an action.
Nice. Here's the book's answer, and I'll read that. And Tori said it a little bit differently, but an outcome is a single result. An event can be a group of results. Got it? Now, theoretical probability of rolling 4. Who can tell me what that is? Explain that to me. This is what we did yesterday. Remember, theoretical probability is a fraction where the numerator is the what? Favorable outcome, and the denominator is the what? Total number of possible outcomes. So, who can tell me what number 2 is? Kalila. Four out of 6? Okay, there's only one 4 on a dice. Okay, I think you're confused with the number 4 with, okay. So it is 1 out of 6 because there's one 4 on a dice? On a dice, okay. Any questions? Captain America, sit down, please. Thank you. Who's got number 3? The probability of rolling a multiple of 2. Jeremy? 3 over 6. You're almost there. You set it up correctly, but we like to have them in simplest terms, or simplest form. So what's 3/6 reduced to? Simplify 3/6. A half. Very good. Last. Who's got the last one? Dave, what's the probability of rolling an 8? If you can't answer this question, we're not leaving out of here. Yeah. It's 0.
Can I go? I'm not a dog.
You can go.
I am short.
I'm timing you, though. If you want to make this your last pass, you better get back here before 3 minutes. Okay, ladies and gentlemen, shh. What you learned: to find the experimental probability and to use the simulations. New vocabulary: experimental probability. Why learn this? Manufacturers collect data on the quality of their products. They use experimental probability to determine how many defective items they can expect to produce. Probability based on experimental data or observation is called experimental probability. So let me get you guys to understand the difference between the two. So you guys remember the problem where you calculated the theoretical probability of rolling a 4?
Yeah.
Okay, and what was that? 1/6, right? Did we actually roll a dice?
No.
Okay, now, I can calculate the experimental probability of rolling a dice and having it land 4 up by rolling the dice, seeing if I got a favorable result. If I didn't, that's first trial. If I keep rolling the dice, doesn't it make sense I'll eventually roll a 4? Right? Now, the experimental probability isn't necessarily the same as the theoretical probability. Let me give you an example. If I did one trial and I rolled the dice and it landed 4 up, that's 1 out of 1, right?
Yep.
That's 100% experimental probability. Is that accurate?
No.
Because I had one trial and it was a successful roll of 4, right? Okay, that's one trial. So if I was to continue, like say roll my dice 100 trials, the experimental probability will get closer to the value of the theoretical probability. Does that make sense?
No.
So if I keep rolling the dice, it'll approach 1/6 for 4.
And for theoretical.
Theoretical, it is 1/6.
So experimental probability is like doing it over and over again. Theoretical is like having it done already.
You calculate it. Okay, experimental is you actually you actually perform the action or the experiment and you record your results. Okay, does that make sense? So just like I said, if I only had one trial, Laura, and it landed 4 up, 1/1, that's a certainty, right? But that's not true, because we know that if we were to continue rolling the dice, a 4 wouldn't always land up, right? Does that make sense? And if we kept doing more trials, our experimental probability would get closer and closer to our theoretical probability. Does that make sense? Okay. Now, here is the key concept. Here's how we calculate the experimental probability. Does it look familiar?
Yeah.
Looks a lot like theoretical probability, right? It's a ratio. Okay. So, here's what I want you guys to do. Here's my problem. If you look, finding experimental probability, you attempt 16 free throws in a basketball game. Your results are shown. What is the experimental probability of making a free throw? So let's take a look at this table, or if we look at I guess I'm gonna call this a legend. 0 represents a what? A missed free throw. 1 represents a what? A free throw that you made. So I need you to calculate the experimental probability. If you will, where's your paper at? Take out your paper and copy some notes down. And it's not going to be until summer that you're going to wish you had those notes. To look back and reflect upon all those fun days in Mr. Hedderly's class. It's like I think there needs to be like a math yearbook. Like a math yearbook of just problems, where students are working on them in class. Who has the answer? This is really easy. You should be able to mentally do this, but I'd like to see you write it out. Joshua, what do you got? You said what? 8/16? And we would simplify that and it would become a half. So 18, if we see here, the number of ones are 8. The number of total attempts were 16, because we have 16 ones and zeros total. So the total number of attempted free throws was 16, and we saw that there are 8 ones, so that means he made 8 out of 16 free throws, which simplifies to a half. Yes?
When you find the probability, can you choose between you want to show it as a fraction, decimal, percentage?
That's a good question. The questions will typically tell you, okay, for this setting up, both of them, you're going to have to set up the fraction, right? That's where you would start. If you want to convert the fraction to a percent because they tell you to find it in a percent or a decimal, then you'll have to move from the ratio, okay? Logan? Sure. Next problem. In 60 coin tosses, 25 are tails. Find the experimental probability. Go ahead. Adepoju, what do you got? 5/12? Did you guys get that also? Any questions? Is this difficult? Okay, now, suppose, have you guys ever gone to the store and bought something and then you brought it home and maybe it worked for a little bit but then it broke? Yeah. So what'd you do? You took it back and returned it if you had the receipt, hopefully got your money back, or maybe you exchanged it out for another because you just knew that it was a defect. Shh. Now, quiet please. It's not unusual for a manufacturer to have defects. And sometimes if the defects are severe, they'll do a recall of the product and fix it. Savannah, could you sit up here, please? Thank you. Sometimes they'll do a recall right here. So here we have a bike company. A bicycle company checks a random sample of bikes. The results are shown here. If the trend continues, which is the best prediction of the number of defective bikes in a batch of 1,300 bikes? So if you look over here, they randomly checked 400 bikes. Of those 400 bikes, 13 were defective. Now, how would I figure out the number of defective bikes in a batch of 1,300 bikes? Any ideas? Trinity. That's how you would solve the way you'd set it up? Take a step back. What are you solving when you do the cross product? What's the word of that thing that you're setting up? It is an equation, and you are going to use cross product, but what do we call that? Do you remember? I'm going to give you a hint. It begins with a P. What equation begins with a P and involves fractions or ratios? Somebody help her out. Khalil, get your girl. What? No. Joshua. Proportion. You're going to set up a proportion. Please turn it off. You're going to set up the proportion, and then you're going to solve a proportion by taking the cross product. Okay? So, can you tell me what your equation was that you set up? Excuse me, ladies and gentlemen. I need you to turn that off now. Quiet, please. Sit down in your seat and stop talking. Slide up one. Don't make me call your people today. Trinity, go ahead. That wasn't a problem before, and now it's a problem? Well, if you want to make it an issue now, you should have thought about that the 3 or 4, 5, 6, 7 classes prior. Sit down. I will call this afternoon on my planning. Trust me. Sit down, please. Stop disrupting my class. Go ahead. You are setting up a proportion there, but that's not the exact one. First, let's figure out the experimental probability. Okay, I can use this ratio, and some students this morning did. It's better if you simplify it, because when you set up the proportion and you solve it, you're dealing with smaller numbers. Okay, so this is the percentage, or this is the proportion of defective bikes in that random check. Okay, so this is the probability of finding a defective bike. Yes? Yes. So the proportion is going to be this right here. If you didn't set up the proportion, I need you to solve the proportion now. It sounds like some of you might have set it up incorrectly. That is the last person that's going to leave out of here until I'm done with this lesson. If you want to keep playing around, there's going to be no more passes. So get your act together. Solve by using the cross product like Trinity just said. Who's got an answer for me? Unisa. Unisa, you said 39? I see Some other people got 39. So when you take the cross product, here's what you end up with. You simplify that. Divide both sides by 100. 39 bikes were defective in a batch of 1,300 bikes. Here's what I need you to do. That was my example on where you'd use a proportion to solve. Now I need to figure out how many defective bikes would be in a batch of 3,500 bikes. Set up another proportion. This bike company decided to produce 3,500 bikes. How many are going to be defective? Jayla, go ahead. 105. Okay, compare your answer with what I got. That's the proportion you should start out with. We're going to reuse 3 over 100 again, okay? We don't know how many are defective out of 3,500, but we're going to use this relationship to figure that out. Cross product, divide both sides by 100. 105 defective bikes. Any questions? We good? All right, a simulation. Let me explain what a simulation is. If you're simulating something, are you really doing that thing? No, a simulation means it's a representation of. Is that right? You guys understand? So in this problem, we're going to simulate 3 family members. Okay, so you have a family. They're going to have 3 children. We're going to assume that it's 50-50, that they can have a boy or a girl. And what we're going to use to simulate the birth of that child is a quarter or a coin. Since it's 50-50, tails, heads, right? So 50% theoretical probability, you're going to land heads up. 50% theoretical probability, you're going to land tails up, right? Does that make sense? So the question says, find the experimental probability that 2 out of 3 children in a family are girls. Assume that girls and boys are equally likely. Okay? Now we're going to simulate the problem by tossing 3 coins. The 3 coins represent what? The 3 kids, right? Heads represents a girl, and tails represents a boy. A sample of 20 coin tosses are shown. So each coin toss, we toss all 3 of them. Do you guys understand? Now, in the first coin toss right here, do you guys see this? How many boys and how many girls here?
2 boys, 1 girl.
2 T's because the tails up represent boys, and 1 H, that means we had 1 daughter, right? I go ahead and I toss it again. What happened here? Same thing. Over here, what happened?
2 girls, 1 boy.
So on the 3rd attempt, 2 girls, 1 boy, and I went ahead and I put red around that one. Why did I put red around that one? That's what we're trying to find out, how many times that's going to occur in my 20 trials. Do you guys understand?
Yeah.
Now, you have to look at the way the question's worded. It says 2 out of 3. It doesn't say 2 or more. Do you see how that would change your problem? It says 2 out of the 3. If it said 2 or more, that means it would include the possibility of all 3 being girls. Do you understand? It just says 2. So you have to read what the question's asking you. So when we continue, take a look at this chart. Take a look at the number of trials, the outcomes from our trials, our experimental trials. What I need you guys to do now is I need you to calculate the experimental probability that 2 out of the 3 kids are going to be girls. What's it going to be? Who's got it? What do you think, Kayla? You look like you're about to answer, but then you decide not to. Can you tell me what you think anyway, though? You don't have any thoughts on where you would start with this? Nicholas, you got any ideas here? What are your thoughts?
Since you have 6 of the favorable outcomes, you put that over 20 because you have the sample 20 tosses, and then you simplify 6 over 20 to 3 over 10.
Very good. So we had 6 outcomes where there's 2 out of 3 are daughters, and then there's 20 trials. And then, like Nicholas just said, we also simplify that. We got 3/10. Pretty basic math. Any questions now? Do you understand what's up? Any questions about this? All right. Now, here's what I need you to do next. I want you to figure out, using the same set of data, what's the experimental probability that all 3 of the kids are boys? So what am I looking for? Triple what?
T.
Okay. How many times did that happen?
Once.
Just once? So what's the experimental probability that all 3 of the kids are going to be boys? 1/20. Super easy, right? Any questions about this? You have a question about this? I'm not letting any more passes until I'm done with this lesson. When I'm done with this lesson. Check your understanding. Vocabulary. What is the difference between theoretical probability and experimental probability? Somebody explain in their words. What is the difference? I don't think I've heard from Nathan today. Were you raising your hand back there, Nathan? You were? Okay, can you go ahead and explain the difference between theoretical probability and experimental probability? I like that. That's how you calculate it, right? Do you remember the formula for theoretical probability? Right. So theoretical probability, you calculate that by taking the ratio of favorable outcomes over total possible outcomes, right? And how is that different from experimental probability?
So experimental probability is like when you take like what you did before.
I like the verb you used, did. Can you kind of explain a little bit more using that, keeping that verb in mind? Think about our simulations. In the warm-up, did we do anything? No, you didn't actually roll the dice, right? So if we were to experimentally determine the probability of rolling a 4, like I gave earlier, okay? You'd roll it and then you'd what? You would look to see if you had 4, so you'd have to observe something. Does that make sense? So in experimental probability, you're actually doing an experiment and observing the results and using that to calculate your probability. So here's what the book gives you. Know this in case you see it on a BCR. Theoretical probability is computed by the formula. The theoretical probability of an event is the number of favorable outcomes divided by the total number of possible outcomes. Experimental probability is based upon data or observation, okay? Now, what I want you to do is go ahead and complete these 2 ratios. You toss a coin 40 times and get 18 tails. Find each experimental probability. Can somebody tell me complete the first fraction? Karis, can you complete that first fraction? Do you know which one's the number of trials? Jeremy, can you help her out? 40. Which one's the number of trials? Which one do you mean by numerator? Which number, the top or bottom? I'm trying to see if you just confuse the two. No, the number of trials, how many times you did something, is the denominator. Okay, so you're right. Your answer is right. It is 22 over 40. Okay, and then could you finish it up? What's this going to be over here? 18 is the number of outcomes where we had tails. That was okay. Obviously, we would simplify these. Okay, but moving on. Bottom number is the number of trials. Okay, we've tossed the coin 40 times, so 40 was the number of trials. All right. If it landed 18 times heads up, that means 14 minus 18, 22 would have been the number of heads. Sorry, I think I messed up. 18 times tails up, then that means 22 times it'd be heads up. All right. Now, I think this is a good question. I'm going to read it to you. I want you guys to try to figure it out. There's a way to mentally solve it. Some students solved it mentally. Some students solved it using a method we discussed earlier in this year and in this lesson. Mental math. In a bird sanctuary, the experimental probability that any bird you see is a robin is about 1/8. Suppose this trend continues. There are 48 birds. Predict the number of robins you will see. Kayla? 6. That's correct. How'd you come up with that? Okay, you multiplied 48 by 1/8, so you took 48 and you divided by 8. Okay. Okay. I would prefer you think about it as a proportion. So 1/8 is equal to x over 48, right? What would be the factor that makes these two equivalent? It would be 6. So 8 times 6 would be 48. 1 times 6 would be 6. So 6 over 48, 6. Okay, but your answer is correct. Who's got this one? This one's a pretty easy one. You want to find the probability that 3 out of 5 babies are boys. You decide to toss a coin to simulate the problem. How many coins would you use? Explain. Kalila. Trinity, can you help her out? Why'd you say 5?
That's the total number of tries.
Not tries. What did the coins represent?
Babies.
Babies. 5 coins, 1 for each baby.